In this video, we will solve a problem that involves Taylor series expansion. This is the 2016 problem from the AP exam. Before we start the problem, let's make sure that we read the entire problem. Always read the entire problem, and then we'll take out all the information. So what it says is the function f has a Taylor series about x equal to 1. So we know that. So it has a Taylor series about x equal to 1, and that the function also converges, okay, within some interval of convergence. Okay, so this is something that we may eventually have to find. Then you've been given the following. You've been told that f of 1 is equal to 1, f prime of 1 is minus half, and you've been given what the nth derivative is nth derivative looks like. All right, so you have all these information. So the first question is asking, what are the first four non-zero terms and the general term of the Taylor series? Okay, so we want the first four terms and also the general term. Okay, so let's go ahead and first write down what a Taylor series expansion should look like. Okay, so f of x, the Taylor series about any the Taylor series for a function f of x about any point a looks like this. It looks like f of a plus f prime at a times x minus a plus f double prime of a over 2 factorial times x minus a square plus so on. The general term becomes the nth derivative of the function evaluated at a divided by n factorial times x minus a to the power n plus dot 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 up to infinity. Okay, so this is the Taylor expansion for this thing. Now, in the problem, we're only asked to find the first four non-zero terms, and we're expanding it about x equal to 1. So in order to do that, what we'll do is let's write down the first four terms. So let's just call it T4. Okay, is going to be equal to f of 1 plus f prime evaluated at 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 square and plus f triple prime over 3 factorial, f triple prime of evaluated at 1 over 3 factorial times x minus 1 to the power 3. Okay, so this would be the first four terms. Okay, the general term would be equal to the nth derivative evaluated at 1 divided by n factorial times x minus 1 to the n and then plus dot dot dot. Okay, so now that we have written out this thing, let us find out the individual terms. So we've been given in the problem that f of 1 is equal to 1. Okay, so f of 1 is simply 1. Then f prime of 1 is minus half, so you can write that down. And we've been told that the nth derivative is given by this formula, minus 1 to the n times n minus 1 factorial over 2 to the n. So the next term, the f prime, is going to be equal to plus, okay, it is minus 1 to the power 2 times 2 minus 1 factorial over 2 to the power 2, okay, and then we're going to divide all this by 2 factorial and then multiply by x minus 1 square. Right, and then the next term is equal to plus, once again we'll evaluate the derivative, which is so minus 1 to the power 3 times 3 minus 1 factorial over 2 to the power 3, and then we have the 3 factorial term here, which is x minus 1 to the power 3, and then plus dot dot dot. Let's write down the nth term, which happens to be minus 1 to the power n times n minus 1 factorial divided by 2 to the n times n factorial times x minus 1 to the power n plus dot dot dot. Okay, so now we can simplify this. The first term becomes 1. The second term, oh sorry, there is an x minus 1 here that I missed. The next term becomes half x minus 1. Okay, the third term we'll simplify. The minus 1 square becomes 1. 2 minus 1 is 1 factorial, so this is simply 1. And then we have 1 over 2 to the 2 times 2 factorial, which becomes 8 times x minus 1 square. The next term becomes minus, okay, minus 1 cube becomes minus 1. 2 factorial, which is right here, so 2 factorial, and then I have a 3 factorial in the denominator, which just gives me 3. So this becomes 1 over 2 cube times 3 times x minus 1 to the power 3, okay, plus dot dot dot. And then the nth term becomes minus 1 to the n. The n minus 1 factorial and the n factorial ends up giving us 2 to the n times simply n, and then x minus 1 to the power n plus dot dot dot. So this would be the answer to the first part of the question, where we have the first 4 non-zero terms and also the general term. Okay. Now, in part B of the question, it asks us to do the following. It says the Taylor series has a radius of convergence of 2. So it tells us this, and it wants us to find the interval of convergence. And so let's show all the work for that. So whenever you're asked to find the interval of convergence or the radius of convergence, you're always going to try to use some test. For this one, we'll use the ratio test. And the ratio test tells us to check this limit. Limit as n approaches infinity, the ratio of the n plus 1th term to the nth term. Okay, and since we already have the nth the term for the general term here, we can apply this in our ratio test, and we end up getting x minus 1 to the power n plus 1 over 2 to the n plus 1 times n plus 1, and then multiplied by 2 to the n times n over x minus 1 to the n. Okay, and when we simplify this, we see that the only terms that end up making a difference are going to be x minus 1, okay, because x minus 1 to the n plus 1 over x minus 1 to the n gives me x minus 1 over 2, and then I have n over n plus 1. Okay, and this, as you take the limit as n approaching infinity, this approaches x minus 1 over 2. This limit, okay, now we see that in order for the series to converge, okay, we want this x minus 1 over 2 to be less than 1. And if that is the case, then we see that x minus 1 is less than 2. So obviously in the problem it said earlier that 2 is the radius of convergence. So we know that r is equal to 2, and this kind of confirms it. And now we can simply see that x minus 1 is therefore greater than minus 2 and less than 2. And then therefore I can move the minus 1 to both sides, and I get minus 1 less than x less than 3. So this happens to be our interval of convergence. Okay. Now to find the interval of convergence, we should also test the function at the two endpoints and see what we end up getting. Okay, so at the endpoints, what do we have? At x equal to minus 1, for instance, we have our series looks like this. Our series is going to be minus 1 to the power n times, so it's minus x is minus 1, so you get minus 2 to the power n over 2 to the n times n, which essentially becomes 1 over n, which is the harmonic series. Okay, and we know that this diverges. So so at the endpoint x equal to minus 1, it does not converge. Let us try at the point x equal to 2. So at this, sorry, x equal to 3. At this point, we have the series minus 1 to the n and 1 to the power n over, oh sorry, 1 to the power, sorry, 2 to the power n over 2 to the n times n, which is equal to minus 1 to the n times 1 over n. Now this is an alternating harmonic series, which we know converges. Okay, this is a series that converges, but conditionally, but it converges. So therefore, the interval of convergence is minus 1, minus 1 less than x less than or equal to 3. All right, so that's the second part of the problem. In part 3, it's saying the Taylor series for f about x equal to 1 can be used to represent f of 1.2. And this is one of the advantages of the Taylor series. You can use this to approximate values, okay? We're going to find 1.2 as an alternating series. It says use the first three non-zero terms of the alternating series to approximate f of 1.2. So what we're going to do is, since we already have the terms from the terms written out in the expansion, we will use the terms to find f of 1.2 to the first three terms, and this ends up becoming, the first term is simply 1. Okay, we have the expansion. The first term is simply 1. The second term is equal to minus, and then it is x minus 1 over 2 factorial, which makes it 1.2 minus 1 over 2 factorial. Okay, plus the third term is x minus 1 square over 2 square times 2, so it is 1.2 minus 1 the whole square over 2 square times 2. Okay, so these are the first three terms, and you can, just calculate this number and see what you end up getting. All right, and you should have something like 1 minus zero point 0.2 over 2 factorial, so which is 2, plus 0.2 square over 8. So these are the first three terms. And the last part of the question, it is asking you to do the following. It wants you to show that the approximation is within 0.001 of the exact value of f of 1.2. Okay, now this is where we'll use the fact that the error in Taylor's, the error is equal to the, oops, this is Taylor's formula. Okay, so the error basically is obtained by taking the next uh, value of the function. So since we are approximating it to the three parts, we'll take the fourth value of the other, since we're using it up to the second order, so we'll use the third value, okay, which will be f of 3. Let's see, which will be equal to simply 2 factorial, no, the third derivative is equal to 2 factorial over 2 cube, okay, which is equal to 1 over 4, and then the error value is going to be equal to the derivative times 1.2 minus 1 cube divided by 3 factorial. And when you evaluate this, you will end up getting 1 over 4 times 0.2 cube over 3 factorial, which happens to be 0.0003, which is definitely less than the error that we wanted, which was in the video, sorry, not in the video, it's 0.001. Okay, so it's definitely less than 0.001. All right, so make sure that you understand every part of this problem, and then the next video we'll take a look at another AP exam question that involves once again the Taylor series.